extended workshop. The work I'm going to talk about today is based on several papers which are all quite connected. So where is the point? Okay. So it's various papers in collaborations with two students of mine, Lorenzo and Passias, a student of James Parks, and also other people in Oxford that I don't have to tell you about them. The outline of the talk is the following. So after a brief introduction, I will move on to 3D supersymmetric gauge theories on curved manifolds, and then I will focus on some examples where one can compute the partition function on these manifolds, as well as have the gravity dual, which was historically how we developed the subject. And then the last two items represent two new results. One has been published over the summer, and one should appear soon. So it's the culmination, perhaps, of this line of research over the past year. So let me just go briefly over the introduction. My main motivation for looking at this problem is the gauge gravity duality, which allows us to study, as everybody know here in this workshop, strongly coupled field theories in terms of weakly coupled gravity. An important ingredient for me is the presence of supersymmetry, because in this case we can then perform very detailed checks of the correspondence, running the correspondence both ways. And when supersymmetry is present in the bulk, then we are led to the study of supersymmetric solutions of supergravity, of your preferred supergravity model in 10 or lower dimensions. And that has been the subject of intensive study over the past 20 years or so. But there is a similar notion of supersymmetry on curved manifolds for rigid theories, so for gauge theories in particular, which leads to similar equations known as rigid Killing-Spinner equation. So, although there is a close similarity, this line here has been studied systematically just over the past year or two. The main motivation for studying gauge theories in curved manifolds, in particular on compact Euclidean manifolds, is that we can compute the path integral exactly in many cases. Not in all cases, but in many cases this is possible, and that's quite remarkable, because we all know how computing path integral is complicated in quantum field theories. And the magic word is localization, so the functional integral over all the field configurations becomes reduced over a smaller set of configurations. In some fortunate cases, it reduces to something which can be really computed explicitly, such as a matrix model. So the saddle point really gives the complete answer, not just an approximation. In general, this partition function, which is denoted Z, depends on all the parameters of the theory, so the parameters that you have in the Lagrangian, as well as the background geometry. Many calculations have appeared in various dimensions, but in this talk I will concentrate exclusively on 3D, which is perhaps the most developed case. So all of these subjects will appear through the talk in a mixed way. I will start from explaining which theories in particular I'm interested in 3 dimensions. So those are theories which have gravity duals, which can be constructed at least when you start in flat space. So the gravity dual for those is known, and I will go through that in a moment. Because they arise from the work volume of parallel M2 branes. And in the past 5 years or so, thanks to the work of Bagger, Lambert, and ABJM, we understood this. So you can consider the simplest model, perhaps, which has a simple gravity dual, is the ABJM theory itself, which is a highly supersymmetric gauge theory in 3 dimensions with Chern-Simons interactions. And certain matter in the bifundamental representation of this gauge group here. K denotes the Chern-Simons level, which appears explicitly in the supersymmetric Chern-Simons term in the action. So for most of the talk, you can take this as your model for the discussion, and we won't have to bother much with generalizations. I'll just make a comment on that in a minute. The gravity dual is the simplest solution that you can think of in 11 dimensions, ADS4 crosses 7, possibly with the quotient by ZK. The simplest in the sense that it's maximally supersymmetric and has been known for many years. Of course, the parameters in the gauge theory map to the parameters in the gravity solution. So we have n, the rank of the gauge groups, which corresponds to this flux, and then k, I already mentioned, at the Chern-Simons level corresponds to this quotient. You can consider generalizations, where the simplest generalization arises from replacing flat space or a quotient of flat space with some Calabi-Yau singularity and placing multiple M2 branes here. And these give rise to plethora of n equal to quiver gauge theories with Chern-Simons terms. So all I will be saying later on during this talk can be applied to such quiver gauge theories. But as I said, that's not an important fact for. So what I really want to explain today is how to deform the background where the field theory lives and how to construct gravity dual to that. So for that purpose, it's sufficient to consider to start with ADS4. So I will not discuss the internal manifolds anymore from now on, which in the Euclidean version, in global coordinates, one can think of this as having a round trisphere at the boundary. So that's really hyperbolic space, in fact. So it was understood already 2-3 years ago how to put an arbitrary three-dimensional supersymmetric theory with n equal 2. So if you have such a theory in flat space, these authors have constructed a recipe for putting the same theory on the round trisphere.
Sorry, one question.
Yeah.
I thought that usual global ADS4 has an S2 cross S1 boundary, right?
Yeah, that's the Euclidean version. So that the Euclidean ADS4, which, as I said, it's just a hyperbolic space. Yeah.
Sphere to destroy specific projection.
Yeah, so in this talk, I will consider field theories on Euclidean backgrounds, whether you like it or not, with their own issues and so on. And therefore, I will be considering gravity duals, which are also Euclidean. So there will be no change of signature in going to the gravity dual. So that leads to a large number of questions and subtleties, but all of the things I'm doing here will be under some control. So solutions can be defined and can be discussed.
On the gravity side, everything will be real, or there will be, after you do this analytical configuration, there will be imaginary flux.
Yeah, sure. In due course, I will mention this issue. Yeah, it's an important issue. I will always take the magic to be real, so I don't want them to change this fact. I can, because in the field theory side, as I will explain in a second, well, they don't appear yet, but the background fields can be complex, so they can be also in the gravity side. And so this leads to some subtleties with the fluxes in the gravity side, but which are under control during this talk. Okay, so what you can put on the trisphere, and the key is the existence of the Killing spinors, which obey this rather simple equation. And in fact, one can obtain a supersymmetric Lagrangian by starting from a Lagrangian of a suitable supergravity in 3 dimensions, in this case would be, and taking a so-called rigid limit, or the coupling limit, where gravity is frozen. So basically there is a systematic procedure for constructing such Lagrangians. Now, using the technique of localization, which I will not say much about today for limit of time. One can compute the path integral exactly. And what I want to emphasize is that the non-trivial part of this path integral is encoded in this special function known as double sign function, which for the particular case of the tree-sphere, here you have just to set this parameter beta to 1, but here I put general beta just in anticipation of what will come later. So, for example, for the ABGEM model, Drucker, Marino, and Putrov have shown originally that if you take the logarithm of the partition function, which we refer as free energy, then in the large n limit, one recovers the famous n to the 3/2, as well as a numerical coefficient, which actually agrees exactly with the computation of holographic free energy in ADS4. So this holographic free energy is nothing but the renormalized on-shell action in ADS4. In fact, various groups, just to mention this briefly, have shown that this is true for more general theories, not just for ABJM, still keeping the S3. So later on, I will be interested in the non-trivial part of the talk will be in generalizing the S3 to some other manifold, or at least to some other metric. So here is where the non-trivial part of the talk starts. And we are interested in putting field theories now with n equal 2 on more general manifolds. So by manifolds here, I mean really different metrics also with different background fields. You may take the same topology of the S3 or the tree-sphere, or you may consider more general topologies. In fact, for most of the talk, I will consider the same topology and just change the metric. So this was explained following the idea of Seiberg and Festuccia was shown in these two papers, that in fact, so long as this equation here has a solution, then one can write down a supersymmetric Lagrangian with all the supersymmetry variations and so on. So the equation here is what in one of my very first slides, I refer to as rigid Killing-Spinner equation. It has the Killing-Spinner, which I denote chi, and then the metric hidden in the variant derivative, and three additional background fields, two vector fields denoted A3 and B3, and a function. Now, as I already mentioned, these fields in Euclidean signature are allowed to be complex. So the fact is that the results about the computation of the partition function and the reduction to the matrix model, which I said it's related to this special sign, double sign function, go through if we replace the round S3 with more general metric. Now, in the literature until recently, two examples were computed in detail. The first one was this by Hama, Kuzumichi, and Lee, and another two examples with the same metric but different background fields, which actually I will expand upon in a second, by these two groups. Although in most of the central part of the talk, I will use this as an example. Later on, and here I'm anticipating that in the recent paper, we computed this partition function for a general metric by keeping S3 topology.
I don't know if it's the right time to ask. If not,
why
I'll
not?
ask it later.
Yeah.
So you mentioned again this imaginary background field,
Yeah.
which on the field theory side is okay because it's just external field.
Yeah.
And once you go to gravity side, as long as you treat gravity classically,
Yeah.
that still is okay. But
Yeah.
eventually we think that ADS-CFT is goes beyond classical gravity. So my question is, when you look at string theory backgrounds, which have complex scalar fields, do you have to worry about unitarity?
Well, you have to worry about unitarity, but in the field theory.
Even
no?
the field theory, right?
So in fact, normally they're not unitary theories.
Right. So okay. So then shouldn't, if I'm a pure ADS-CFT guy and I believe that I have a unitary string theory on one side, and it is dual to, should be dual to some field theory. I guess that one way you can say is that you are extending ADS-CFT correspondence to basically
I think this is a
defining it
very
in
big
way.
question, but I don't know the answer to that.
But that's okay. I just wanted to understand. So that's really the issue in all constructions of your type.
No, the first issue which I know how to deal with is to construct solutions where the fields are complex. That's already non-trivial because you want the real metric. So in this context, I know how to do that. Then if you want to quantize that, I don't know what to do.
Right. See, the reason why I'm saying is that if you play these games and you insist on having real fields, then you do not have a match between ADS-CFT and localization.
Why?
You just don't. You do computation exactly the same ones that you did. We can talk later about that.
Yeah.
But you do exactly the same computation, computer partition function using Paston's formula, and then you just compute a renormalized Euclidean action again. But you do this in a setting where everything is real, and so you believe in sort of vanilla ADS-CFT duality, and they disagree.
I think this is too much detail to continue
Sure,
here.
but I just wanted to understand that
Yeah,
in your
I mean,
case,
you are probably referring to some specific example that you know very well, which I don't know, so we should talk later. In my case, I can get agreement.
yeah, I know your case.
But certainly there are still many issues which I'm not claiming everything is understood. So, okay. So I will use the case of the biaxial squash trisphere as an initial example for illustration of some main features. In particular, we can then have the luxury of a very explicit and simple metric, which is almost the metric on the round sphere. There is one single parameter, which I take to be real, called S, and in addition, it turns out that there are actually two inequivalent set of fields, which happen to be also of specific type, so they are also real or purely imaginary, in fact, with which one can preserve supersymmetry, meaning that there is a solution to this equation here. So the recipe for constructing the Lagrangian and the localizing terms then involve replacing the flat space covariant derivative, where curly A denotes the gauge field, with a coupling to the background fields. And that's not enough. One has to also add new couplings to the Lagrangians. Moreover, one has to write down terms that are using to perform this localization trick. And typically, they look like this term here. Therefore, it's automatic that they vanish if and only if delta psi is 0, which is the supersymmetry variation. So they localize on supersymmetric configuration. The two backgrounds, which I just mentioned, involve, as far as A3 is concerned, these two expressions. So they are quite similar, but they differ in the specific coefficient here. Which is not arbitrary. So you cannot just put here an arbitrary coefficient function of S, say, but just two specific ones, given the metric which is fixed to this form. So the squashing parameter also enters into the gauge field. And also the function h turns out to be just a simple constant related to S. So one can compute the partition function. These two groups have computed that. And in fact, it turns out that in one case, in this case here, the partition function turns out to be the same as the one of the round sphere, which was, well, a fact, but not quite explained until, I think, recently, but now we understand why. Well, the other one gives a non-trivial answer. So it involves this SP function, which I mentioned, with a non-trivial B related to this parameter S. In fact, the relation is simply this one. So if you take the large n limit, of course, in one case, you just get the same as the round sphere. And in the other case, you get something quite simple. You get the result of the round sphere multiplied by this term here. Okay, so this was the prediction of the field theory. And we wanted to understand whether it's possible and to construct gravity dual and to reproduce the properties of this field theory. In particular, to reproduce this result for the partition function in the large n limit. So one can phrase the problem as a fielding problem, with the way we like to discuss it. So we have a manifold which is topologically a three-sphere with a certain metric, the metric, the biaxially squashed sphere, also known as Berger metric. And we want to find a fielding, so a metric on a four-dimensional manifold, which will turn out to be just a ball. So you just field the inside of the three-sphere. We want to preserve supersymmetry. And then we want also to have some field. Gauge field is a natural gas that reduces to these vector fields on the boundary. Yeah.
If you start with the Festuccia-Seiberg way of obtaining the supersymmetry version of this method, sorry, the supersymmetry formulation of this kind of manifold, does A3, A mu 3, and P mu and H have any particular meaning coming from the supergravity?
You mean, sorry, you mean coming from this supergravity?
No, from the other one.
The other one. Well, the other one, there are some background fields in this off-shell formulation of the supergravity. So one has to use this so-called mu minimal supergravity, which actually in 3 dimensions has not been developed until recently. So this, in particular, this paper of Closet et al., that they've written down all the Lagrangians and everything explicitly. So yeah, there is another paper which I don't remember, but it has to do with writing this new minimal supergravity in 3 dimensions. The old one in 4 dimensions, I think, was due to Peter West and collaborators. So they are auxiliary field in that context. But we will recover them from these dynamical fields of this particular supergravity in 1 dimension more. So we are now in 4 dimensions, as you can see from here. And the action that we consider is that for just gauge supergravity in 4 dimensions, so there is, in addition to the Einstein, Hilbert, and cosmological constant, there is just a term for the gauge field. So here I don't put subscript superscript 3 to distinguish that from a 3-dimensional field, whereas this is a 4-dimensional field. Well, that was just a working hypothesis that we can find the gravity dual solutions within this model here. And the main motivation is that we can then uplift these. If we find such solutions which are supersymmetric, we can uplift them to 11 dimensions by using known formula due to Gauntlet, Varela, I think mainly to them. Okay, so we have this problem. We have to find this manifold with a metric and a gauge field with this requirement here, which I already mentioned. And in the end, if you want, you can put this as a requirement, or you can put it as a check. In the end, you want to check that the holographic free energy agrees with the computation in the field theory. So this is the pictorial view of what one wants to achieve, which also shows you the result in this case. So we find that the manifold in this case is so-called Taub-Nut ADS with its metric, which has been known for many years, I guess. And the gauge field turns out to be a self-dual gauge field, which is possible in 4 dimensions. So you can have this metric, which is Einstein, in fact, because basically the stress energy tensor of F drops out from the equations of motion. Also, of course, there is an explicit expression for the gauge field, but here is not important. Of course, the metric and the gauge field depend on the parameter S. the holographic free energy involves a standard computation in 4 dimensions. We don't have to worry about logarithmic terms because we are just in even dimensions here. And we have to compute the usual terms, the Gibbons-Hawking, the counting terms to remove the divergences. And then we have to compute both all terms in the action, namely this part, which then reduces just to a volume because R is proportional to a constant, and the kinetic term for F. Well, if you do that, in the end, you find that you get agreement with the gravity side, with the field theory side, and also the case of the first case, or the so-called 1/4 BPS, which gives the same result as the round sphere. It's a non-trivial agreement because all terms that you have around all depend on trivially on S, but then in the end they combine and give something which doesn't depend on S. And the other one gives exactly the same numerical coefficient as in the field theory side. So we get agreement for these examples. So the next thing I want to tell you is that, and I can regard this as an important intermediate step, is a generalization of these examples here, which appeared in a paper with my student in June or July. And I think, although that was just another example, it was very instructive. So I'm going to discuss some features of this example, and then I will use that to motivate the final part of the talk, where I will summarize the results of the paper on vocalization and some results to appear about the general structure of these solutions. So before moving to the example, let me just remind you briefly something which historically should have been the first, but for convenience, I've not discussed it so far. So the ellipsoid discussed by Hama, Hosomichi, and Lee has this matrix here, which manifestly just preserves U1 cross U1 isometry, not SU2 cross U1. And it has some specific form of background fields. And if you plug all of these into this Killing-Spinner equation, it preserves supersymmetry. In fact, the way they constructed that originally was not because they didn't have this equation. It wasn't known at the time, so they just constructed it from trial and error. Nevertheless, the computation of the partition function goes through, and it gives essentially the same form of the partition function as in the other case. So there is still this SP function appearing, this double sign function. So the example with my student was an example which, well, we could write it down everything explicitly, although it does not fit anymore in just one line, but basically in a couple of lines, as you will see from the next transparency. So there is an explicit metric which depends on 2 parameters now. For example, we can call them B and A. And there is this function here that appears explicitly here. And there are also gauge fields. So here I'm just, for the moment, discussing the 3-dimensional background metric. So there is some change of coordinates to do, which involves these parameters V and A, in order to write the metric in some coordinates phi1 and phi2, which have well-defined periodicities, which is important to study the global properties of the metric. And then there are some background fields, which here actually I didn't bother to write explicitly, this AI and VI. There are some functions of theta. Now here coming to an issue which was already raised a couple of times. It turns out, and that's the first example that we had in explicit form, that these fields are all complex in general. So they can be complex. Namely, they're not just real or pure imaginary, but they really are genuinely complex. And that because this parameter Q, which will appear in the next slide, as a function of V and A, is something which manifestly can be complex. Nevertheless, the metric is not complex, is real, and smooth. So, yeah.
You're saying it can be complex. Can they also be real?
Yeah.
And there is a non-trivial check that you can do.
Well, there is a non-trivial plot which I will show when they're real and when they're complex. Okay, that's the plot. So if this the axis is v square and this axis is a, this dark part is a region which is not allowed because the metric becomes singular. So let's just forget about that. And the solutions are defined only in this positive wedge, which goes off to infinity. And they are real here in this shaded region, and up here, whereas in this bulk part, they're complex. Why? Well, just because that's the simplest pictorial way to look at when this parameter becomes real or imaginary or complex. Okay. Actually, the way this picture is presented is also to highlight the fact that these two axes, so this positive imaginary axis, positive v square axis and this segment here for A, they represent the previous solutions. So this one represents the solution of the ellipsoid, whereas this one corresponds exactly to the case where we get the biaxially squashed sphere. So that's a two-parameter generalization, which, well, as I'm going here through all details, but we don't have to go through the details of the formula. It doesn't matter. Just the message is that this comprises these two examples as special cases, and it's a more general example, which in fact, as you can see from here, already that conveys the idea that things here are real, whereas in general they're not, although you have just looked at the formula to convince yourself of that. Very good. So, well, why did we consider this example and not some other example? I mean, after all, there was a specific metric. I mean, we could have done something else. The reason, the main motivation, is that this example, when you look at it, comes together with the gravity dual. So understanding the background metric in 3D and understanding its gravity dual is a process that one has to do at the same time for this particular case by using basically previous results in the literature. In particular, we could extract those metrics from some known metric by Plebanski and Demiansky, which are solutions to Maxwell-Einstein supergravity. So in particular, we impose that they are supersymmetric and so on and so on. The gravity solutions, which I'm not going to write here because that involves an even longer expression for the metric, but they're all self-dual metric again, so they're all Einstein metric with the topology of the ball. And therefore, as a comment, which I'm not expanding upon, but if this is the case, then you can always uplift to M theory without any subtleties. And then all these different gauge fields, they correspond to, in all cases, they correspond to different instantons. Now, as a partial answer to the concern raised already, although the metric is real, and the complex, the field, the instanton is complex, it drops out of the equations of motion, luckily enough, so there is no contradiction into that. So that's just something at classical level. So I'm just saying that there is a solution like that. It's not an approximation of any kind. Incidentally, this issue, it becomes much more serious and something I'm struggling with for many months if you try and do something similar in 5D, but that's not the topic of today. And maybe this is something we can discuss later.
That's exactly
Yeah. Right, so in this case, it's okay to do that. And we can move on to the holographic free energy. Again, one can compute it by using the same formula. And one finds that it depends, although everything depends non-trivially on V and A, so specifically the metric does not depend just on this parameter Q. Let me remind you what I meant. So the metric depends on V and A because they appear here. However, the free energy in the end conspires to depend only on one parameter, one particular combination of them, which is Q, which incidentally it's the parameter which can be complex. So the free energy itself can be complex. And in fact, that of course reproduces the old results in the special cases. So after some inspired change of variable, then one can show that the free energy takes this expression, which was the same that was known before in the previous cases. So it depends only on one parameter. Although my metric and background fields depend on two, the free energy that in the larger limit depends only on one parameter, which enters exactly in the same way as before. So this might be just an accident, and then we don't have to discuss anymore. Or it might be something true in general that inspires further work, which is the case. So we conjecture that, in fact, the full partition function on these particular backgrounds can be written exactly as a matrix model which involves this function, which we know that in the larger limit would give this result. So here, the gravity side just tells us something about the larger limit. It does not tell us what's happening before taking the larger limit. But I'm just saying, I suspect that this is going to be true even if you don't take the larger limit. So how do we check that? In order to test that, we should have computed explicitly the partition function. So we should have done all these one-loop computations and so on. We should just change hat, put away the gravity hat, and put some field theory hat, and do the computation. Well, that looked a bit complicated. However, well, we decided to, in fact, do the computation in full generality, because although that background was just depending on two parameters, but it didn't have some particular symmetry or something that we could use, as has been done, as say on the round sphere. On the round sphere, you have to compute the determinant, so you can compute all the eigenmodes explicitly. Okay, fine. Even if you have SU2 isometry, you can do the same. But as you start having less and less symmetry, then there isn't anything special about the metric. So, in fact, we correctly suspected that one can do the computation in general. And so one can take a general metric of this type, and here we made a simplifying assumption, which might seem like unmotivated, because I just explained to you that I had complex fields. But in order to get to the answer, here we just assume that the fields are real as a technical device for doing the computation more quickly. I think it's just a technical point which can be relaxed, and the trick to do the computation will just go through. In any case, it is true that we assume here in this particular computation that all the fields are real, and that already implies that there is a U1 isometry. So essentially, without any loss of generality, we could consider a metric of this form where this psi parameterizes the isometry. And otherwise, the function omega c and the one form A are arbitrary, and you can just take anything that you want, provided that the metric is smooth. So it's really, you can take any shape that you draw on the blackboard, you can plug it there, and then you can do localization with this. The key fact that we understood, and that was in fact already motivated by the gravity result, is that one can pick an arbitrary Killing vector. So here phi 1, d phi 2 are a basis over U1, so over torus, U1 plus U1, parameterized by just two real numbers. And while this determines an almost contact structure, in the sense that there is a one form that you can consider out of the metric and this Killing vector, and some other geometric information, which I'm not going through. But importantly, it fixes all the remaining background fields. So once you fix a metric, and you fix this Killing vector, then all the other background fields are fixed. So that specifies completely the background. And after some calculations, of course, the result, surprisingly or not surprisingly, well, in a sense remarkably, although perhaps not surprisingly, is the same exactly the same as the one that was known before, and here I guess it's the first time I put it on in its complete form. And the non-trivial part of this partition function is here, is hidden here into this special function which I already brought quite at the beginning. So this was already written, but the non-trivial fact, and this is the result, which takes a lot of computation, is to show that this beta is given by the ratio of these two numbers here. So that basically solves the problem of computing the partition function of in general. So there is nothing anymore to compute for the tree-sphere. That's the general result, and it depends just on this ratio here. Let me just make some remarks without actually explaining any detail. The computation is done generalizing the method of Hama, Hosomichi, and Lee of pairing eigenvalues. So that's easy to understand in words. One has to compute the determinant of certain operators, which are very complicated, and well, because they depend on this omega and so on, you don't even know explicitly what they are. So it looks hopeless. However, because of the magic of supersymmetry, essentially one can show that there are many cancellations, and the only contribution which remains comes from those terms which are not cancelled, and they obey simple equations, so one can essentially solve the eigenvalues for these unpaired modes explicitly, and that gives the result. So the dependence of the metric, I mean, to cut the story, to really go to the bottom line, the partition function basically does not depend on the metric. There were also a couple of papers of some students, I guess, or something, where they do some other examples, a little bit weird because they did it after our paper. But in any case, there is one specific example where they point out that one can use a round three-sphere metric and still get a non-trivial partition function. But that's obvious from my discussion. You take here the round sphere metric, and but then you take B1 and B2 different, and that gives you a non-trivial partition function. Or any other metric you want. It doesn't really matter. Obviously, this agrees immediately with the large N limit, so with the conjecture we made with Achilles Passias, which was one of our motivations. So in the last 7 minutes, perhaps, I want to finish the talk by just mentioning some work to appear, hopefully in the next few weeks, where we take the next step forward and we go back to gravity, and then now we have computed the full partition function on any metric, and then we can ask two questions, at least two questions. One question is, given an arbitrary metric on S3, together with the choice of this almost contact structure, etc., such that it preserves supersymmetry and such that my partition function is true, can I construct its gravity dual? And the next question is related to that, is given such a metric, assuming such a gravity dual exists, can I compute the free energy of it in general and show that it agrees always with the partition function? Well, these are two very obvious questions. And in fact, we can give a quite general answer to that, again, with some simplifying assumptions, which are, I think, they're just technical points. But basically, if we again restrict ourselves to minimal gauge supergravity in 4 dimensions, so if you ask me, do these solutions exist outside this context, I don't know the answer to that. They could. Or do these solutions exist if you don't assume anti-self duality? Again, they could. But so far, all the examples we have, they were all constructed within this case. So it is quite plausible that they will cover an open set, say, a dense open set on the space of all possible solutions. So let me just explain how these solutions are constructed. So here there is some wordy description, and then the next transparency, some formula for the experts. So we can start with a self-dual Einstein metric with the U1 cross U1 isometry, and these were studied by mathematicians, in particular by Calderbank and Pedersen, and specify to be on a manifold with the topology of the 4 ball, whose conformal boundary is a tree-sphere. So this can be written explicitly or semi-explicitly in the sense that they involve some functions in some specific coordinates. It might be sometimes it's quite tricky to go to the coordinates that you want, but in any case, they can be written down, and this paper is all about constructing these metrics. Then, given that we have U1 cross U1 isometry, we can pick a Killing vector, where phi1 and phi2 are a basis of this torus. And this is analogous, and in fact, it's dual to the choice of contact structure on the boundary. I mean, the same U1 cross U1 that you have in 4 dimensions, obviously you will have on the boundary. So it's exactly the same torus. And in this case, the choice of Killing vector induces a conformally related Kähler metric. So although we start with self-dual Einstein metric after a conformal transformation, which is in fact completely specified by this choices vector field, the related metric is Kähler, also with vanishing Rich's scalar, although it doesn't seem to play an important role. And there is a specific complex structure. And in addition, there is a specific instanton, namely a gauge field F, which is self-dual. So it obeys F equals tau F. All of that is fixed once you choose this Killing vector. Combining all of this together and using results by these authors here, part of which are or were in Cambridge, one sees that this preserves supersymmetry. So it is a supersymmetric solution. Right. So this is how one does the construction. A little bit more in formula. One has a Killing vector and constructs a 2 form out of this Killing vector. The conformal factor I alluded to before is given by the norm of this 2 form. And one can show that the metric always takes this canonical form. Finally, the gauge field A, so the gauge field of the instanton, is just given by essentially this so-called Ricci potential, which is the 1 form such that its curvature is the Ricci curvature. So all of this is just making in formula what I already said, just to say that it's not something random, it is some specific recipe. Very good. And finally, and quite interestingly, one can compute. So we managed to compute the holographic free energy. In fact, this computation is done completely independent of any construction of metric. So we have shown that this formula is true, and it's the formula which is coming from the Lagrangian limit of the partition function in general. So you don't have to know even the metric to conclude this. So in a sense, that's sort of the end of the story in this particular subject, because you don't have to use the metric, so there isn't anything else to check. So once, if you ever find a metric, then you already know a priori that the free energy that you compute from it can depend only on B1 and B2 in this form. Oops, what I'm doing. What happened? This was just things which were not supposed to appear. Only in case someone was very interested. So sorry about that. I was saying that, so for this computation here, we have assumed only that the solution exists. And basically, this is similar, it's analogous to the results that some years ago with Sparks and Yao we obtained in the context of Sasaki-Einstein geometry, where one can compute the volume of a Sasakian manifold. And in fact, that depended again on some B, for people that remember those papers, and that is again this, it's related to a contact structure. So it's really, really analogous. And again, you didn't know the metric in general here, and the fact that we get agreement of this formula with the formula from field theory in general, without independently of any specific metric on the boundary, in the gravity side, it's again analogous to the fact that that was a general check of A maximization and minimization of volume minimization of Sasaki-Einstein manifold in ADS5 CFT4. So that's the, I would say that that's the analogous result for ADS4 CFT3. And with that, question?
Yeah. So in this case, when you are computing this holographic free energy, in some cases, it can be reduced to a boundary term.
Mm-hmm.
Is that the magic that's happening?
Almost, yes, almost. But there is also contribution from the interior. It's quite, that's the subtlety. Yeah.
Right.
Yeah, although,
For generic metric, that's what I would expect. There will be a bulk piece.
yeah, there is. Yes.
Okay.
So, and then there are basically only these two pieces.
That's right.
And they contribute magically into this form. I mean, it's magic in the sense that you don't know the metric.
Right.
So-
you have been able to, that's what was my question. So even though it's not just the boundary term, there is also a bulk contribution.
There is a bulk contribution that, again, you don't know in general, but the part that you want, you know, you can extract from global properties. Yeah, it's quite nice.
Yeah. Very nice.
Okay, I was going to conclude with this, so thank you.
So you assumed a U1 cross U1 symmetry,
Yeah.
whereas that's stronger than what you need for supersymmetry by itself. Can you relax this assumption and still have localization? Or?
You're asking this question in the field theory or in the gravity side?
Well, either, I suppose.
Either. So the fact that there is U1 isometry, let me talk about the field theory side, but in fact the gravity side is, I think it's completely analogous, comes from the technique, so the true assumption is that the fields are real. That implies that there is a U1 Killing vector, and then assuming that there is a second is not really a big assumption, because basically the case where there isn't, it's a case which can be dealt with in a different way. So the question is that what happens if you don't assume that the fields are real? In general, you will not have a Killing vector, and therefore the methods that we're using here are are not directly applicable. However, something which I suppressed, when we are in Euclidean and we study these Killing spinor equations, we have one equation which is some d alpha plus something chi equal to 0, and then there is also another equation for another spinor chi tilde, which is usually explained as follows. This chi and chi tilde would be complex charge conjugate in Lorentzian signature, but in Euclidean signature they are not anymore related. So this equation here, that in Lorentzian signature would be just taking this equation and doing charge conjugate of that, in Euclidean signature is not true. It's an independent equation. And in particular, if the fields which appear in these dot dot dots are complex, here they will have some different fields. And this is an independent spinor. So the case we have done, we have considered, where we assume that everything here is real, corresponds to the fact where the case where chi tilde is really the charge conjugate. So what I want to say is that although I've never discussed, there is an additional spinor, chi tilde, which satisfies this equation here. But in this case, it's trivial because it's just the charge conjugate. So what I'm saying is that in general, when this is not true anymore because the fields are complex, we will be able to carry out the same computation if we assume that there is another solution to this equation here. So then, well, there is some technical comments, but basically there is some vector bilinear which you construct using these two, which is a Killing vector. And I think, well, although I've not looked at the detail, I think that the same is true in the gravity side. So also in the gravity side, we will want to study solutions where there are now two spinors, one obeying one equation and one obeying an appropriate other equation. Then we will have a Killing vector. So yeah, I think this is what happens. If you don't have that and you have complex fields and you don't have this spinor here, then it's quite possible that these methods will not work because you don't have you don't have any symmetry at all.
Komagorski and collaborators have classified the backgrounds that are supposed to give you supersymmetry.
Yeah.
And they have shown that the free energy can depend only on special types of moduli. Are you in agreement with these types of claims?
Of course. I mean, they are in agreement with us in the sense that we have computed the explicit answer, and well, we have given to you the formula.
But they don't assume anything about isometries. They looked at the most general.
Yeah, that's true. That's true. They look at the most general, but then they don't know the answer. They tell you the partition function, whatever it is that they don't know, can depend only on this B1 and B2.
Right. Which
If you phrase it in,
which eventually, of course, says that even in the most general case, that's the result you should get.
well, no, it doesn't tell you that.
If you have only these modulus, yes, I thought.
No, they tell you on what can it depend. They don't tell you how it depends.
No, that I agree. Yes.
Well, I mean, okay, they tell you z is a function of b1 and b2. And here I tell you, if you assume this condition you want, then this is the answer. I mean, then you can use it for whatever application you want. Yeah, well, I think